Hello and welcome to this session on Geospatial Deep Learning with ArcGIS. My name is Rohit Singh. I am the lead developer of ArcGIS API for Python and the director of Esri's R&D center in New Delhi that's focused on geospatial AI. And joining me is Vinay Viswambharan, who is the product manager for image analysis and AI in ArcGIS. This is going to be a demo-rich session, so wanted to start off with a quick session overview so you know what's expected. We'll start with an introduction to what is AI, what's machine learning, and how it's related to deep learning. And then we'll look at the deep learning workflow in ArcGIS, going from the imagery to training your own deep learning models and using them within ArcGIS Pro, as well as using the ArcGIS Learn module of the Python API. Then we look at the different types of deep learning models and how they can be applied to imagery and remote sensing. We'll see how you can use image server to scale up the processing and use these models on a large geographic area. And finally, we'll end with some resources to help you get started. So with that, let's get started. Today, AI is at the peak of the hype chart, and if you were to go out and look at what's happening in this industry, there's a lot of buzzwords, a lot of terminology being thrown at you, and it's easy to get lost and feel intimidated. But it really isn't that hard. I'd like to parse it down to three important concepts, starting with AI or artificial intelligence that describes the ability of machines or computers to exhibit what we typically associate with humans. That could be things like understanding speech or seeing things, computer vision. Machine learning is one way to achieve AI. It's based on data driven techniques where the machine or the computer is looking at a lot of existing data and learning the patterns needed to come up with a prediction when it sees unseen data that it's not seen. And deep learning is one type of machine learning that loosely resembles the human brain. It's based on deep neural networks with several layers of neurons, and where these networks figure out by looking at the data what the outcome should be, what the predictions are. So that's one way of looking at machine learning and how it's a superset of deep learning. But there's another way, and that's how about contrasting traditional machine learning with deep learning. How traditionally machine learning is different from the newer deep learning techniques. And that's in this example on the top, you can see how there's an image on the left that's of a car, and the machine is trying to figure out if it's a car or not. And typically, there's a human in the loop with traditional machine learning techniques. Now, in the case of computer vision or really classical computer vision, it was human data scientists who were creating things like edge detectors or blob detectors. And once those features or edges or blobs or corners were extracted from that imagery, we used to apply a machine learning algorithm. It could be a support vector machine. This diagram shows how a shallow neural network could be applied to come up with a prediction of whether it's a car or not based on those extracted features. Now, wouldn't it be great if the network or the model could do this task by itself just by looking at the raw data? If it can figure out what those important features should be so it can come up with the right predictions. And that's exactly what deep learning does. In deep learning, the deep neural networks figures out or learns what it needs to learn to come up with the right predictions. And to me, that's the beauty of deep learning. So you may be wondering, well, all that's great, but how does it relate to ArcGIS? Now, in ArcGIS, we've had machine learning tools in the broad areas of classification, clustering, and prediction. And now we have a rich set of tools for deep learning, going from preparing your data to training a wide variety of deep learning models to using them or inferencing, detecting objects or classifying features, classifying pixels, and doing post-processing things like non-max suppression that Vinay is going to talk about later. So why should we be using deep learning for imagery tasks? Well, the short answer is that computer vision is now almost as good, if not better, than human vision. The chart on the right shows the results from a competition, the ImageNet Visual Recognition Challenge, where a computer was shown an image and it had to come up with a prediction of what's in that image. And till 2012, it was machine learning algorithms that were winning that competition. And the error rate used to be above 25%. So one in every four times the machine got it wrong. Since then, since 2012, when the first deep learning algorithm AlexNet came, it's been deep learning networks that have been winning this competition, and they have been getting so good that sometime in the last few years, they even started exceeding the human accuracy. So, computers are now better than humans at tasks like classifying images. They got so good that they actually had to discontinue this competition. So with that, now let me hand it over to Vinay, who's going to tell us how deep learning can be applied to solve a wide variety of problems in GIS. Over to you, Vinay.
Thanks, Rohit. Now, from an imagery perspective, there are four key tasks or four key categories of deep learning. First is pixel classification. Typical example is land cover classification. Next, we have object detection, and as the name suggests, designed to detect objects of interest within images. Cats, dogs, for instance, but from a more practical standpoint, it would be cars, planes, and other structures. The third is instance segmentation, where users really want to get precise polygonal boundaries of each object, in this case, building footprints. Lastly, object classification, and a typical example is classifying a structure as damaged or undamaged. ArcGIS natively supports each one of these deep learning models. Now, ArcGIS supports end-to-end deep learning workflows. We have tools for preparing training samples, prepping data to train models, model training tools, and tools to perform inferencing. We support the four key categories of deep learning that I just talked about. That's pixel classification, object detection, instance segmentation, and image classification. We will be showing you examples of all of these through both ArcGIS Pro and Notebooks. And lastly, you can run all of these deep learning tools using ArcGIS Pro, the map viewer, or using Notebooks. Now, if you want to run this on desktop, the licensing model is you need ArcGIS Image Analyst extension. And if you want to scale out your processing, you can run it in a distributed environment. You can use Enterprise. And for this, you need ArcGIS Image Server license. Now, breaking it down, here's the workflow within ArcGIS. Step one is you collect training samples. Step two, using the export training data for deep learning tool, you generate chips. Step three, training the neural network. And last step, using out-of-the-box tools, we can run inferencing. Now, let's go through each one of the steps. Step one is collecting training samples. There are different types of capturing training samples or label data. First is you could use ArcGIS Pro, the editing tools that are natively available within ArcGIS Pro, or the map viewer, or you could build your own custom applications using the JavaScript API. Next is you could use the training sample manager, which is historically available within ArcGIS Pro for classification workflows. What we've added in ArcGIS Pro 2.5 is a new experience, the label objects for deep learning experience. This is designed specifically for deep learning workflows. Now, there are three information models when it comes to, or multiple information models when it comes to capturing training samples. If you're a local user, if you're working on the desktop, you're a single user, you could capture training samples using a feature class. Now, if you want a more collaborative experience, you have multiple users who are writing to the same feature service or simultaneously capturing training samples, you can use a feature service. And lastly, depending on your workflows, you could also use a classified thematic raster as an input for providing training samples. The next step, step 2, is essentially exporting the training samples to image chips. These chips will then be used for training the model. This can be done using notebooks, using ArcGIS API for Python, or we can use GP tools from within ArcGIS Pro. Step 3 is where you train your deep learning model. We support a variety of models, which we will talk about a little later. You can train your model using ArcGIS API for Python, and you can also train deep learning models using geoprocessing tools natively within Pro. And that's something that we've newly added within ArcGIS Pro 2.5, the ability to train deep learning models natively within Pro. We also support external deep learning frameworks, so you can easily tie into TensorFlow and CNTK and similar frameworks. Last step is inferencing. We've extended the capabilities in this release to support object classification as well. We've previously, in the past couple releases, we've had object detection and pixel classification. And inferencing can be run both on desktop, or you could use Enterprise to run inferencing. To recap, we've used tools to generate training samples, which are used to train a model using tools and APIs. This produces a deep learning package, which can be used for inferencing using Pro and Image Server. And the intermediate file, like I said, is a deep learning package. So what is a deep learning package? A deep learning package, or a DLPK, is essentially just a zip file that's automatically treated by the training tools, created by the training tools. It contains the model definition files, the train model, and optionally it creates a custom Python raster function for inferencing. The custom Python raster function is if it's a function that's not natively supported within ArcGIS. The DLPK can be shared across the organization, enabling users to easily reuse the model for running inferencing on their imagery. Now here's a tabular representation of the 4 key pieces that I just talked about. And these are the different clients that are available. On the left, you see ArcGIS Pro, ArcGIS API for Python, Map Viewer, and Image Server. And here you have a representation of all of the tools, how they're accessible and available. At a higher level, here's the deep learning workflow. In addition to the deep learning pieces, ArcGIS enables efficient management of large volumes of imagery. This is done using mosaic datasets and image services. Next, ArcGIS enables advanced analysis of the deep learning results. And these results can then be used in field mobility and monitoring applications such as ArcGIS Workforce and Operations Dashboard. Now I'll dive into a demonstration where we'll go through the entire deep learning process using ArcGIS Pro. Now keep in mind, some of the demos we will show you today are scenarios you've probably seen before, but this time they're all being run natively using ArcGIS Pro or using notebooks with a much more streamlined workflow in place. So to provide you with a little context about the scenario, here you're looking at the NAPE imagery. It's 1 meter resolution imagery, and what we really want to do is identify pools within this location. Step 1 is you need to capture training samples. Like I said, there are multiple ways you could do that. One of the options is using the label objects for deep learning tool. Invoking the tool gives you the option to specify new classes, or you could simply just start digitizing features. and so on. Now, the export training data tool was available in the past 2 releases. To make the user experience simpler, we've embedded it within the label objects tool. So you can directly switch to this tab and export the outputs or create chips directly into a specific folder. These are default parameters which you could just use by default. Optionally, you could head over to the geoprocessing tool. Under the image analyst toolbox, you have a bunch of tool sets and tools, and we can invoke the export training data for deep learning tool. In the interest of time, I have pre-populated all of the parameters. Here's my input raster, the output folder where the chips will reside. Here's an input feature class, and this is where you define the value. You can provide a mask if needed, and here are additional parameters. Once I run my process, the output is a bunch of chips in addition to metadata. This folder then goes into the training tool. So I can call the train deep learning model tool. This is my folder that contains all of the training chips which we created in the previous step. This is the output model that is going to be written out. You can specify the number of epochs, and you really don't need to specify these parameters. We use intelligent defaults, but in case you want to tweak parameters, you can change the backbone model. You can change the validation percentage, basically the number of chips that you want to use for validation of your results, and you can change the model type if needed. Once you run this, now depending on your resources on your machine, if you have a high-end GPU, the process obviously ends a lot faster. You could complete the process a lot faster. The output is a trained model. Once you have that, you can call your inferencing tool. We have a variety of inferencing tools. In this case, I want to detect pools. So I specify my input raster, which is my nape imagery, the output detected objects, which is a feature class. Here's my model definition file, additional parameters that I can specify, including the non-maximum suppression set of parameters, which defines how to handle overlapping features. Once we run the tool, before that, here's just a quick representation of all the training samples that we've captured. Once we've run the tool, here are all of the pools that have been detected within our area of interest. So a matter of clicks, we've gone through 4 key tools to actually go all the way from capturing your training samples, exporting these training samples, training your model, and eventually detecting objects. So that was our end-to-end workflow that was doable directly within ArcGIS Pro. Now I'll hand it over to Rohit, who's going to be talking a little bit about the Python API.
That was great, Vinay. Analysts can now use geoprocessing tools to perform the complete deep learning workflow, including training your own deep learning models without leaving ArcGIS Pro. But not everyone, myself included, likes to use tools all the time. Data scientists prefer to do their work in notebooks and use Python code and libraries. And for that reason, at ArcGIS Enterprise 10.7, we introduce ArcGIS Notebooks that lets them use the rich set of open source Python libraries such as TensorFlow, PyTorch, and Keras for deep learning, and combine them with ArcGIS using ArcPy and ArcGIS API for Python. And now with Pro 2.5, Python notebooks are seamlessly integrated right within ArcGIS Pro. Python is the lingua franca, or the most commonly used language for data science, and ArcGIS API for Python allows analysts and data scientists to bring in all the rich capabilities of ArcGIS into the notebook. And we've recently added the ArcGIS Learn module that enables analysts and data scientists to easily train and use deep learning models with a simple intuitive API. Now, if you're a sophisticated data scientist, you can use any deep learning framework such as TensorFlow, CNTK, or PyTorch to train your models, provided you know a lot of math, linear algebra, and calculus, you know how backprop works, what loss functions are, and so on. Training a model can involve dozens of lines of code, and it can be complicated. You need to figure out how to install these libraries. And believe me, it can get pretty complicated with all the downstream dependencies of each library. With ArcGIS Learn, training a model is super easy. It's typically the same 3 to 5 lines of code that you need to train a wide variety of models. And if you're using ArcGIS Pro 2.5 or ArcGIS Notebooks, all the dependencies can easily be included in that environment. And it's not just about training. ArcGIS Learn supports the full deep learning workflow, starting from exporting the training data to training a wide variety of models ranging from object detection models, object classification models, to pixel classification, and now to models that can be used to extract entities from unstructured text or even process 3D data such as point clouds. It also has tools to deploy these models, manage them, and use them to derive insight out of imagery. ArcGIS Learn is closely integrated with ArcGIS. It's built for ArcGIS. It directly consumes the exported training data from Pro, and the models that it creates are directly usable in ArcGIS. It has a wide variety of models that can be trained using a consistent API. It uses intelligent defaults. So these are some things that we've figured out that makes it suitable to train models on satellite imagery, but it also gives you the flexibility to override those defaults when needed. And because it's built on top of Fast AI and PyTorch, which are popular deep learning libraries, it leverages the latest research in deep learning to train very accurate model using very simple code. There are a lot of enhancements and goodies that we've added on top of it to make it sweeter for use. And here are some of the things that you can do today with ArcGIS Learn. This slide shows a sprinkling of the different variety of projects that we've accomplished using ArcGIS Learn. It's best seen through a demo, so let's do that now. Okay, so now let's see how we can use ArcGIS Learn to perform land cover classification. In this example, we'll be using data provided by the Chesapeake Conservancy and train a deep learning model that can go from the Esri world imagery to the classified land cover. Now, Chesapeake Conservancy went through this process, and this is actually a very labor-intensive process. In their case, it took them 10 months where analysts produced a high-resolution land cover data, and by the time they completed, the land cover changes, and this was done for 2013 and 14. So how can we use all of the effort that they have put in to label that land cover, use that as training data to train a deep learning model? So given new imagery, it should then be able to come up with the updated land cover classification. So what we've done is that we've taken data from this project for Kent County, Delaware, and loaded that in ArcGIS Pro. So let me switch over to ArcGIS Pro. Here we are looking at the Esri world imagery for Delaware, and let's bring in the downloaded data, the classified land cover from Kent County, Delaware, and zoom into this area of interest. Now this land cover has been classified such that the houses are showing up in the red color, the roads are showing up in the black color, the water bodies in blue, and so on. So what I'm going to do is train a deep learning model to go from the Esri world imagery to the classified land cover, and we'll be using this data as training data to train our model. And that starts with exporting the training data. So And the input raster, we are using the Esri world imagery. We specified an output folder where image chips will be generated. And this is the Kent County classified land cover obtained from the Chesapeake Conservancy. We are using exporting the image chips only for a small area of interest because I want to do it live and don't want it to take a whole lot of time. So let's just do it for the small area of interest, choosing the TIFF file format, giving the chip sizes, and the metadata format. The chips should be exported as classified tiles. That's the input format that an image classification or a pixel classification task requires. So here I'm kicking off the export training data, and let's switch over to um, uh, Windows Explorer. Going to that folder, we see that the data has been exported. And here, deep learning models cannot just process all of this data at once, this huge raster. It has to do a lot of computation, and that happens on GPUs that have limited capacity. And for that reason, we chip out the data into these small fragments and use them for training. This is the chips for the world imagery, and here are the chips for the labels or the classified land cover. And now I'm going to switch over to a notebook where we'll be training a land cover classification model. It's right here, and this is the code that we'll be using to train our model. What I've done is that from the ArcGIS Learn module, I've imported the UNet classifier. That's a UNet model used for pixel classification tasks, and the prepare data method. And I've pointed the prepare data method at the chips that we just exported. And this can, load in all of that data and applies random transformations such as randomly zooming, rotating, and flipping those images to create more data, more synthetic data from those image chips. That's a way to create a more generalizable model. And here we are visualizing a small batch of that data. Now you'll notice how we have overlaid the uh, land cover classification on top of the satellite imagery. So if I give a lower transparency, the labels are showing up with a lighter color. So this is just visualizing a small batch of that data. It's already in a format that's ready to train. And here I'm creating my UNet classifier, passing in that data, and my model has been instantiated. So with a new model, let's see if it can come up with the predictions. Given the satellite imagery, can it come up with the right predictions and do the labeling? And here we've got the ground truth on the left and the predictions on the right. Now, as you can see, the predictions don't match the ground truth at all. And that's because the model has not been trained. It's like an untrained model, and it needs to be trained. It needs to be fit to the data. And I'll do that using the fit method. And I'm training the model, making it fit to that data over 5 epochs or training passes over the entire training data set of those chips that I just exported. Now, I'm also passing a learning rate while fitting, and to pass in that learning rate and the significance of that learning rate, I want to use, while the model is training, I want to explain what a learning rate is and how I pass that in. So you can imagine that, a deep neural network, when it's first instantiated, is like a newly born brain. It really doesn't know anything about the world, and it needs to look at several examples and learn from them. Now, if it learns at a slow rate, it can take forever to learn anything. But if you give it a very high learning rate, the model can be quick to jump to conclusions, if I were to uh, put it loosely. In a way, in mathematical terms, it doesn't find the optimum value where the model converges, where the error is the least. And to find the optimum learning rate at which the model can learn, we actually provide a handy tool which is based on top of FastAI's learning rate finder. What it does is that it starts training the model at a very tiny learning rate and keeps increasing that learning rate. And at some point, the model begins to learn and the loss or the error begins to go down. Model is learning and the error is going down. And at some point, the learning rate becomes so high that the loss starts going up again. At that point, it's too high for the model to learn. So what we do is we can pick a value where the loss is still going down and pick a high value from that. In this case, it's 1e negative 3 or 0.001. The loss is still going down. It's not high enough that the model will diverge or won't learn anything. And it's still fast enough that I can do it live in front of you while giving this session. So as the model is learning, as we are fitting it to the data, we also print out the loss on the training data and the validation data. So what does that mean? Well, what we do is we take about 10% of the training data and set it aside. And we don't use it for training. We only use it to validate or check how good the model is. So when we are checking the accuracy of the model, we are only doing it on data that the model has not seen. And in the third column, we are printing the accuracy of the model over each training epoch. And we can notice how it's taking about 47 seconds for each epoch. And with each training epoch, you'll notice how the loss or the error rate is going down both for the training data set and the validation data set. And the accuracy is going up from 55% to now 77%. And let's see how much it is after the final epoch. And hopefully the model would have trained enough that we'll be able to visually see that it's beginning to learn the major land cover classes. So we are about done, and it should complete that last epoch any moment now. And we ended up with close to 76% accuracy. And now we can run the show results method once again and see if the model is doing better than the results we got earlier, where the predictions were very different from the ground truth. And as you can see, in just less than 5 minutes and 5 training epochs on a small amount of training data, I have been able to train a model that's able to identify the major land cover classes. It's able to now starting to recognize where the buildings are. It knows where the forested areas are, where the shrubland is, and where the roads are to a little extent. Now, training a more accurate model is all about giving it more training data and training it for longer over more epochs. Once you are satisfied with the model, you can save it out, and that creates a deep learning package that you can use for inferencing. Now, in the interest of time, I've already trained this data for longer, and you can see how the accuracy went up, and it's now close to giving much better results. And here's another model that was trained on all of that data from Chesapeake Conservancy, and you can see how it's so good that the results are almost as good as the ground truth. It's almost a perfect match. So once we've trained our model, we can go back to ArcGIS Pro and use that model to find the land cover in a new area. And I'll do that in this area of interest and switch off the labels for a little while. And as you can see, if you notice closely at this row of houses and this path here in the current world imagery, you can see these. but when this data was labeled by the Chesapeake Conservancy, this was missing. So most likely these houses were still under construction, and that's why they were not labeled as homes and the path. Now, when I used a well-trained model with the classify pixels using deep learning tool, I was able to pass in that trained model in the path here in the model definition. In the input raster, it's the world imagery, and we can then pass in the layer, the output raster. So when I did that, I'll just show the results for that. I was able to arrive at this inference land cover using the deep learning model, and it's now able to give me the updated land cover based on the current world imagery. So that was an example of how ArcGIS Learn can be used to train a deep learning model for land cover classification. Now I'll hand it over to Vinay, who's going to talk about the different types of deep learning models and how they can be applied to GIS. Over to you, Vinay.
Now, a few more demos. I'll talk about the first model. This is the most simplest, which is image classification. And the models supported here are Inception, ResNet, and more. Typical scenarios are classifying pools as clean or unclean, or classifying structures as damaged or undamaged. All right. So to provide you with context, the scenario here is the Woolsey fires that occurred late 2018. What you're looking at is the fire perimeter. And what I really want to do here is classify my structures as either damaged or undamaged. We have about 10,000 buildings in this AOI, this area of interest. Step one is capturing training samples. And we do the same process. We go through the same process. We label objects using deep learning. We call the label objects for deep learning user experience. And these are a bunch of training samples down south that I've captured. Once we have these tools, once we have captured this, we can invoke the export training data for deep learning. You specify your input raster, your output folder, similar to what we had done before, similar parameters. Run the process, and we have a set of chips. These chips then go into your training, into your trained deep learning model geoprocessing tool. You specify your training data, which is your chips, additional model parameters, and you'll notice previously it was just object detection, but in this case it's object classification because the system automatically recognizes the chips, the metadata in the chips, indicating that what we're trying to do is object classification, and accordingly it populates this dropdown. Once we run the tool, we get our model, which we can then use for inferencing purposes. And this time it's not object detection, it's classifying objects using deep learning. We provide an input raster. Our building's features is an input. The output is the building features classified. Then we have a model definition file and a class label field, and we can run the process. Once the process is run, here are the results, 10,000 buildings that have been classified as damaged and undamaged. Zooming in a little tighter, you can see the classifications are accurate. Now, the real value of doing deep learning within ArcGIS is the geospatial side of things. You have access to the complete ecosystem. So in this case, what I do is I take these results, these feature classes, I use them as barriers in Network Analyst, and then we identify shelters that are within, or locations where we can have shelters that are within 20 minutes walk time. This is what the results look like. right? Now, once we have this, you can monitor your project for any given area. Here's a customized operations dashboard. Here you get a dynamic representation or a dynamic view of the average damaged buildings, the total number of damaged structures, undamaged structures, and you could populate it with any additional parameters you need based on how you enrich your data. So that was a good example of how we went all the way from raw unstructured imagery. It was managed using image services, and then we went through the deep learning process, used the results in Network Analyst to provide additional insights, and lastly, we pulled it into an operations dashboard to get a higher level overview of the project. Now I'll hand it back over to Rohit, who's going to talk a little bit about pixel classification.
So when I just showed how these homes could be classified as damaged or not, and he was able to do that by applying an object classification model. And what it did is looked at this layer of existing building footprints. And for each building footprint, it looked at the imagery around it and classified that image as damaged or not. But what if we were missing building footprints? There can be missing data such as here, or if there were newer developments, such as in this case, in this region. Could we use the existing building footprints as training data to extract these building footprints for areas where we do not have them? Well, sure we can, and let me show you how we did it. What we did is we exported training data from the existing building footprints, which has been overlaid on top of the imagery here. You can see the existing buildings showing up in the pink color here. And we've trained, once again, a unit classifier model, this time to extract those building footprints. So given the satellite imagery, it should find which pixels belong to buildings and which do not. So once again, we are training a unit classifier model, the same training methodology, find an optimum learning rate, fit the model to the data. And after doing that, let's look at the results with the ground truth on the left and the prediction on the right. And you can already notice even in the first image chip, there's actually a building in the top right corner, which was missing in our label data that the model has been able to pick out. And here's another example where this building was actually missing, this one as well, but the model is good enough to find them as well. So it's at least as good as the human annotators who labeled that data. And this time for performing the inferencing, we actually used image server with raster analytics capability. All that was needed was getting the imagery layer. And to process this imagery, we actually did this processing at a larger area of interest. All we need to do is call the classify pixels method. And in this case, we use a 4-machine raster analytics cluster consisting of cloud GPUs with 24 GBs of memory each, and processing a large area of interest covering over 60,000 buildings only took 20 minutes. That's a rate of generating 3,000 building footprints every minute. So let's switch back to Pro and look at some examples of the kinds of footprints that were created. Now, because this is a pixel classification model, it's only classifying each pixel as belonging to a building or not. The results are not perfect. And that's where the post-processing tools in ArcGIS come in handy, using which we can go from those masks of buildings to regularized building footprint using tools that we've built just for this purpose. So let's look at the results of the regularized footprints. And you can see how deep learning has done such an excellent job at extracting these footprints just by looking at the imagery. Now, this is an example of a pixel classification model. known as the deep learning world as a semantic segmentation model, where we are assigning a label to each pixel of that image. For example, here the pixels belonging to the cat are in the yellow color, the pixels belonging to ground are green, and so on. And this can be very useful for GIS for doing things like land cover classification that we saw earlier, or in this case, for extracting building footprints. Now, for the next type of model, let me hand it over back to Vinay.
So next, I'm going to show you a demonstration, couple demonstrations on object detection. There's one I'd already shown you, which was detecting pools. And again, the types of models that we support are single shot detector and retina net. Applications include detecting trees, cars, airplanes, so on and so forth. So in this case, our demonstration is going to be detecting well pads. Okay. Now, the scenario here is I want to understand and visualize trends in drilling activity over the Permian Basin. So you're looking at the Delaware Basin, and at 10-meter resolution sentinel imagery, you can clearly see well pads across the landscape. This image, the sentinel image, is great for change detection. If you compare two images over two different time periods, you can see new well pads have emerged, changes in frac ponds, new construction sites, and here you have new well pads as well. Now, what I really want to do is identify change and detect objects over a much larger area. And given the booming rate of development, this could be a daunting task. And here's where deep learning really comes into play. So again, going back to a set of processes, step one is you capture a bunch of training samples. Here we have a bunch of training samples that have been captured. Yep. Once we have the training samples, you can run the export training data tool. Then you train your deep learning model. And lastly, you detect objects using deep learning. You invoke the tool that will detect the objects. Zooming out, here are our results. And I actually ran this through a series of tools. So what it gives me at this point is going to be set of well pads. You can see how it's increased over time. So we've got 52 slices of imagery, and what I really want to see is how the number of well pads have increased over time. And you can see this change gradually. So there again, we used deep learning and we brought in the geospatial aspects. We could step through time and see changes. Now we could visualize emerging patterns over this area also with respect to space and time. And here you can see increasing hotspots or increasing cold spots, which shows you increasing activity or emergence of new well pads. Once we have this, again, you could take this to the next step. You could see the total number of well pads for any given day. And you can monitor activity near your lease. You can see the total number of active well pads, frac ponds, and you can even filter based on a specific type of asset. All right, now I'll hand it back over to Rohit, who's going to talk about instance segmentation.
Okay, so Vinay just showed us object detection models, and we typically use object detection models when we want to find the locations of objects, in the form of bounding boxes. Now, there's another type of deep learning model architecture. This is known as instance segmentation models. And I like to think of them as more precise object detection models in that not only can they give us the location of objects, but they do that in the form of polygonal, with their polygonal boundaries. So you can see how in the example on the left, not only do we find these cars, we also find the precise boundary of each car. And in the example on the right, it could be used to find the boundaries of building footprints. Now, you would have noticed how earlier I used a UNet model, a semantic segmentation model for finding building footprints, but that would not work in cases where buildings are contiguous. So let me switch over to my browser here to show you what I mean by that. If I were to use a semantic segmentation model, I will only be able to find the pixels that belong to buildings and those that do not, and I would not be able to find each instance of the buildings. And that's where instance segmentation models come in. We can differentiate each instance of the object and create polygonal boundaries for it. Now I'm also using this opportunity to show us the guide for ArcGIS Learn. You'll find it in the developer site for ArcGIS API for Python in the Deep Learning with ArcGIS section. And here's an example where we are using a mask RCNN model, an instance segmentation model, to bring in the data for building footprints from Berlin, where buildings are right next to each other, especially in the city center, and we want to find their precise boundaries and create separate building footprints for these. So the same training methodology once again, but this time we are creating a mask RCNN model, finding a good learning rate, fitting it to the data. And let's scroll down and look at some results. So you can see here the ground truth on the left and how the predictions very closely match the ground truth. It's able to delineate each individual building footprint. And we took this model. You can also make it predict the bounding boxes as well. So you can use it in both modes. We use this model to extract footprints, and here are the results. So you can see how when there's a row of contiguous buildings, like here, the mask RCN model is able to delineate each individual building. And if I were to move here, there are these U-shaped buildings, and turning off the the vectors for those building footprints, you can see how the model really had to look at each building, see their boundaries, and how this would have been like such a labor-intensive task for a human to do, and how deep learning can really automate this task. So you must be wondering, like, how can we take such models and apply them on a large geographic area, automating this task and saving a lot of human effort? And for that, let me hand it over back to Vinay.
So now I'll talk about scaling deep learning using ArcGIS Enterprise. Deep learning is an intensive process, and depending on the system resources, it can take a while to run. ArcGIS Enterprise can be used for scaling your deep learning process, and the central component or technology enabling distributed processing is the raster analysis server, which essentially is an ArcGIS image server that's configured in a raster analysis role. Now, once configured, a raster analysis server will be able to handle raster processing in parallel by leveraging multiple GPUs. Leveraging multiple instances of raster analytics servers helps speed up what otherwise might be a very long-running process. Here's a sample enterprise architecture, and this was used for a project internally. First of all, on the left, we have the ArcGIS portal. That's your standard enterprise portal. It's connected to an ArcGIS server on Azure, which hosts that portal, but also talks to the ArcGIS data store, which is what enables you to publish hosted feature layers. So this is the data store that contains all your feature outputs from inferencing. Then on the right, you have your Azure hosted image server and Azure hosted raster analysis server. And as I've mentioned, the raster analytics server is still an image server, just assigned to an array role. And finally, you've got your distributed raster data stores as well as Azure Blob Storage that the image servers have direct access to. Now, when it comes to deploying models, you can really deploy any type of model you want with any kind of framework, provided all the requisite dependencies are installed in the array servers. When we perform inference, we utilize ArcGIS Notebooks or Pro, and to run the model, as you recall, it takes a single function call via Notebooks or a single tool from within ArcGIS Pro. After running this model, we get back a feature class, detected objects, and these get stored back in the ArcGIS data store. When it comes to scaling up inferencing, there's actually no hard limit on the number of raster analytics servers you want to use. It really depends on the size of data you need to analyze. Here's an example of scaling processing using raster analytics, detecting building footprints. This took us about 4.5 hours on a Pro instance with a single GP100 card. Scaling the process using raster analytics brought down our processing times to 20 minutes. That's a significant gain in performance. So, summarizing and the key takeaways, ArcGIS supports end-to-end deep learning workflows, all the way from capturing training samples to running inferencing. We support the key deep learning categories within ArcGIS. We support a variety of model types, and we showed demos for most of them. The deep learning tools are accessible through the platform as GP tools and ArcGIS Pro, through ArcGIS Learn modules in the ArcGIS API for Python, and it's also available as raster analytics servers to be run through image server. Lastly, your deep learning processes can be scaled massively using image server. This is a bunch of resources which will definitely be useful for you. There's a ton of content that's available for developers and users alike. Join our GeoNet community and Geo-AI blogs as well on Medium. So that's all we have time for, and thank you so much for attending. Thanks.